If you're up in the next minute, I'll hand back your test. You were up here earlier. Yeah, but plus this will do it. So we'll head back to the rest after class. What? So welcome everyone. So we have the test graded and we're handing them back, but in order not to disrupt class too much, we'll hand back the rest after class. So come up after class and I'll hand back the rest. So let's look at the schedule one more time. So today is the last day before spring break. Hopefully you all turned in your homework on frequent items and streaming stuff. So hopefully it was less time consuming than the first few. The next homework should be kind of somewhat in a similar regime. The regression one will again be worth 100 points. I think it's out. So we won't have, I won't have taught everything in here until after breaks, but you can get started. So you can get started on that one. These two will mainly be designed to be done like in MATLAB. It's a little bit easier to do some of the stuff in MATLAB. You can do it in Python or something else if you want, but it's going to just be a little bit easier to do it in, at least it was designed to originally do in MATLAB, but you can do it in other languages if you want. Yeah.
So you said both assignments will be posted after the break?
This one is posted, I think I posted it correctly this afternoon.
Okay.
I haven't double checked everything. So it should be up, you can get started on it, although everything that will cover stuff in a couple of these lectures after break that you'll probably want to do before you finish it. I might be flexible on the deadline, although I don't want to make it too close to when the final report is due. So we can discuss that after break, but you can probably get started on some of it and start planning out how much time you need at least.
So starting on this regression assignment, is easier to use MATLAB, right?
Yeah, so these two are kind of, they're going to be doing things with matrices, and there's, I guess, it's a little easier in MATLAB. You can probably do them in Python or something else fine, as long as you have good matrix libraries for it. But I actually give you a stub of code in here in MATLAB. I mean, it's like 3 or 4 lines I give you, so it's not going to be hard to write in another language, but yeah, so it might be a little bit easier in MATLAB. You can use Octave, it should work just fine, so you don't need MATLAB. Octave is a free version you can put on your computer. So also the intermediate report is due, let's see, it's due Monday after break. It's due at noon on Monday after break. I want to make sure that you guys have it done, because we're going to have the second half of the lecture on Monday is going to be an in-class discussion where your groups are going to be put in clusters of size 2 or 3. And so you'll discuss there, and you should bring copies of your report into class so you can hand them out to aid in the discussion. Also, you should be signing up to meet with me roughly in these 3 days here to get an overview of your, I can give you feedback based on your intermediate report based on that discussion. Again, bring printouts of all the 3 documents you would have turned in up to that point. That'll just make that a little bit easier and more efficient. Okay, so And then before we moved around some lectures a little bit, these used to be after break. Not totally sure why I moved them. I think it's a little bit better this way. So I'll be talking today about L1 regression and lasso, but we will break from that part. I think we'll finish it with about 20 to 30 minutes left in class, and we'll switch to kind of an ethics-y-like discussion about the use of p-values. And so if you haven't heard p-values, I'll start by kind of defining what they are and what are some of the common issues, and hopefully we'll have some discussion about this. And then we'll talk more about some very large-scale alternatives to these SVD and and matrix inverse type approach for solving these basic regression dimensionality problems that we can scale these up. There's some cool kind of tricks here as well. So we'll do this after break for a couple lectures. All right, and then we'll switch to some noise and privacy discussions and some graph analysis to finish up. Right? So after break, we have like 4 weeks left, and things will be moving pretty quickly. All right. Any questions on the schedule before we get into the lecture? All right. Okay. So so the lecture today is on this lasso and in general this so regularized regression. And so what this is about is where hold on a second. Need to hopefully my pen will start working again. So what this is about is starting with this linear regression problem and then adding a regularization term and okay. So hopefully this comes back. Great. Okay, so we're going to start with this. The input to the problem is going to be a set x, y, where each xi in x, each xi is going to be a point. I'll just call this lowercase x. It's going to be x0, x1, up to xd, and y is going to be some scalar value. And what we're going to do is try and build a linear function that's going to take in a value of that looks like x, maybe without the first 0 coordinate. We're going to fix x0 is always equal to 1, and this will have this offset thing, and we're going to find this f alpha, which is going to map to a point in R, where f alpha of x is going to be equal to the sum equals I equals 1 or 0 up to d of alpha 0 x0. And so to define this function, it's a linear function. I'm basically, not starting at these i's. So it's a linear function here. This is equal to alpha 0 plus alpha 1 x1 plus alpha 2 x2. Right, so this is this nice simple linear function. We need to find these alphas, right? And in general, our goal was to find so the alpha in our defining our function f alpha was equal to our min alpha, or say alpha prime, or let's make this alpha star, where I can do this x matrix times an alpha vector, right? Alpha is now alpha 0, alpha 1, up to alpha d, minus y, L2. Right, and this was equal to our min alpha of, let's see, sum over I j equals 1 to n. These are all of the data points in x of x. This would be the, let me write it this way, xj in x, xj dot product alpha minus y squared, yj. So I compare the jth value of y in this y vector. And we have right. So if I look at the jth value of y, I compare it to this function. This is equal to f of alpha of xj minus yj squared, right? So I'm looking at the sum of the squared errors, right? So this is just to refresh your memory that there was this nice solution for this. And if I set this up as a vector at x, then I can, ends up, there's this nice clean form, closed form solution. So there's a matrix x appropriately with the ones in the first term there. There's this closed form solution that looked like this. So there's this nice closed form solution that solved the L2 loss on this linear regression, right? For every x value, which is a d-dimensional or d plus 1 dimensional, I try to match the y value that I found by a linear function. Okay, and I can solve for these coefficients in this closed form. Right, so this is what we talked about. And so if we add regularization, then what we're doing is we're adding a term that looks something like this, where we have some coefficient that tells us how important this regularization is. The larger, the more importance this gets. And this says, I want to minimize this whole expression, but I want the alphas, my coefficients of, in my function to be small. So I'm going to penalize them for being large. And we looked at either a 1 or a 2 norm here. So I either looked at the 1 norm or the 2 norm over here. The 2 norm is ridge regression, and there's still a closed form for 2 norm for ridge regression. I can say x transpose x plus it's going to be gamma squared. I need a identity matrix here. Gamma squared identity matrix. This inverse x transpose y. Right. So if I do the ridge regression with the 2 norm on alpha, I have a closed form solution. If I use the 1 norm, there's not a closed form solution, but I said the 1 norm is going to guarantee some sparsity effects. That's going to have some advantages to it. Okay, so the point of the lecture today is to try and kind of talk through why this regularization in general is useful, and really what's going on. How do we get sparsity out of the 1 norm? And by sparsity, I mean that if I use a 1 norm here, this is called lasso, then I get sparsity in alpha. This means many of the alpha j are going to be equal to 0 exactly. So the solution I find will have many of these coefficients exactly equal to 0, which kind of says some of the dimensions, some of the attributes of the data are not important or not useful in predicting the outcome. Or at least they're not useful once I have the other non-zero ones. Okay? Before I get into kind of, there are a couple of explanations for this. Okay, so why do we want to do this regularization? There are a couple of ways to think about this. So one is that high slope is unstable. Okay, so if I have data that looks kind of like this, and I fit, right, and I've got x and the y-axis, I fit some curve through here, and the slope is kind of high here, right? So then what I'm doing is if I change, like this axis here is representing x, if I move to a different, from x to x prime, then it's going to create a large difference here in the value. Because I change it a small amount in the x-coordinate, the y-coordinate changes a lot. So kind of small, large slopes are kind of unstable, so the regularization is biasing towards smaller slopes. This is kind of a natural thing. Another thing that can kind of be seen here, because this includes this offset, is that I'm also biasing towards the mean of the data. Okay, so if I look at what this offset is telling me is that if I have a small slope here, let's say I have a slope that's small, right? Like I keep the same offset, so it's going through what happens when the x is a 0, right? I keep the same offset. This is kind of this alpha 0 term. Then it's what that's kind of doing, if I've centered it left and right at the same time, I'm kind of going through the mean of the data. I'm kind of averaging towards the mean. And that's saying that if I kind of know where the middle of the data is, and then I change the x coordinates, by default, if I don't think there's a pattern, then I should have the same thing for all x coordinates. Should kind of keep it flat. If I don't think there's any sort of there's any relationship at all, I think it's kind of meaningless to think as I move in one direction, the score should go up. If I don't think that's there, it should be completely flat. So I'm going to again try and bias towards that, and that's again a smaller slope. There's this idea that you can kind of relate to this called regression to the mean. So who's heard of this term thrown around before? Okay, so I'm guessing you guys, it turned out, pay attention to sports. Maybe we've heard it, maybe in politics. This sort of thing where if there's I'll be very generic here, a sports player, that's what we call them, right? So sports player, there's a first half of a season and a second half of the season. Let's say over their career, they've had some score that they generally get, and the first half of the next season they do extremely well. You kind of expect, well, that's unlikely for them to. It's more likely that they're going to go back to their average in the second half than what they continue doing in the first half. And that's kind of saying, well, I saw some data points that said, oh, I should be over here. I'm a much better player than I was before. But says, well, maybe I don't trust that so much. I'd rather trust the prior information better. And kind of, so I'm more likely to come back down to what the mean of it was. Right? There are other ways of kind of seeing this where if you see some data points that say, oh, this is really going great, well, often if you see more data points and they're that aren't going to necessarily continue being great. You might just happen to be picking out the outliers in the first part, and you shouldn't expect that they're necessarily going to continue to be outliers. And this kind of gives a regression towards the mean when you do this regularization going on here. All right, so this is another intuition for kind of what's going on. Yeah.
I'm just trying to form an analogy. Would it be okay to say that the average score for soccer games is 2 goals per team? And let's say the scores are in the first few minutes versus the scores are the goals are spread out across the game. So is that a good
Yeah, so, let's say that there's correlation within a soccer game and that some teams are higher scoring, so, but it's commonly used that way, at least when you hear people talking about it, that in the first half of the soccer game, if there are a lot of goals, you might not expect as many in the second half. The reasons for that, people may call it regression to the mean. That's probably not what it is. It's probably they go into a defensive style of play or something like that. But it could mean they're actually two high-scoring teams, so you expect them to score more in the second half as well. You'd be careful when you say this to use it. This regression to the mean is a real phenomenon, but it's a little, I don't want to get into all the details about it, but it's kind of related to what's going on. Okay, so if you've heard that before, that's kind of what regularization is doing also. Okay, so these are kind of some initial intuition. I want to give a bit more geometric, mathematical view of what's going on here. Okay, so let's look at I went the wrong way. Okay, so let's look at this this formulation again. Argument alpha of x alpha minus y2 plus s alpha 1. Okay? So this is the lasso formulation. And so a useful thing to point out, and this will hold true with the ridge regression as well with the L1 norm, is that I can look at an equivalent version of the problem. It's equivalent to another problem, which is arg min alpha x times alpha minus y2. And now I'm going to say true such that alpha 1 is going to be less than or equal to some value t, where t depends on x, y, and s. Okay, there is some t, there exists some t, such that there's an equivalent formulation that'll give us the same answer. Okay, so I can say, I want to find the one that minimizes the L2 error, but I want to put a hard restriction that the L1 norm of my alpha coefficients is bounded by t. So I'm going to have a hard upper bound. I say the L1 norm cannot be bigger than some t value. And that's equivalent to solving it for some s value, where I put a regularization. I just penalize it. So I'm changing this kind of the cost function in some way. If I think about there's some space, some d plus one-dimensional space of alphas, and I have some cost that's everywhere in the space, and I'm finding the minimum of this cost function. And in the top version, it looks like I'm completely warping this cost function in some strange way. The second one, I'm saying it's the same cost function, but I'm only allowed to look at certain values of alpha. Right, so I can think of a picture here where I've got, this is the space of alpha, d plus 1, and this is, so I'm going to have, and this is somehow the cost, right? And so the regular one, this one here, this is a typical L2 cost. It's going to be a parabola. Somehow it's going to look like a parabola. It's an L2 function. It's a sum of squared errors. They always look like a parabola in some way. Anything you're adding, so there's going to be some minimum here, and I want to find this minimum. going to have some restriction. Maybe, let me fix this here. But I'm going to have some restriction. I can't use this point the minimum because I must have the alpha values. This is alpha equals to 0. That the L1 norm can't go past here. This is somehow like t. So the minimum I'm going to find is then going to be here. So this is going to be alpha star. Okay, and so now I'm going to say that there's this other cost function, so this green one here, which is going to have its minimum here, and it's going to have no restriction. Right, so this one had this restriction. I could only consider this region here. The green one has no restrictions, but it's going to have the same minimum here, or this same. It may not have the same cost. Maybe this is deceiving here. The cost might not be the same, but the minimum point is going to occur at the same spot. Okay, so if I can find the minimum of the blue one or the green one, and so it turns out if you're just using optimization to find this, the green one is easier to work with. If you want to think about the geometric meaning of this, the blue one is easier to think about. Okay. Sometimes you can plug in like an LP, and then it's useful to look at the blue one for optimization as well. But yeah.
So both of them are convex functions? Oh.
Yeah. So they're both going to be convex, and it turns out that this domain for the blue one is also going to be convex, and we'll come back and see this, and that's important. So both functions. I mean, the blue one is clearly convex. It's an L2. It's a typical L2 function. It's convex. It's just we're restricted. We can't look at solutions over here. We have to look at these solutions. Yeah. Okay, so why is this? And this is true for whether I use the L1 or the L2 regularization on alpha. Why is this true? Well, I can do something like I can solve it on the green one, and then I can figure out what the L1 norm of alpha is in the green solution, and I set that equal to t. That turns out to be the right solution. So I can always do this. As s gets smaller, t gets larger. As s increases, t decreases. At some point, like if I get out to here, t no longer ever needs to increase. So there's no point in ever increasing it. And that's basically when s is equal to 0. If s is equal to 0, then the green function and the blue function are the same. And there's no point in increasing t any further because the optimal solution is the optimal solution. Right? But up until then, it's going to be different. Okay. Okay, so let's look at the geometry of this a little bit differently. Okay, I added them in the wrong order. I'll fix that later. Let me just mention that you can basically solve for alpha using some version of orthogonal matching pursuit. Like before with this compressed sensing, we had a binary kind of alpha essentially was the signal we were trying to find before. Now it's a bunch of coefficients, and a lot of them might be 0. And so again, we can set them one by one in this procedure, and this works pretty well. Or we could do this version where I solve every time I know the choice of the, I know which coefficients are active, are the ones which are non-zero, then I can solve for the best choice of alpha for for each of those dimensions. Okay, and so it's useful to think about this approach. I'll mention quickly, and I won't describe in full detail, just because it's kind of tedious, and we'll talk about other stuff in the class. But it's good to keep this in mind. What am I doing here? I'm choosing the one dimension, the one coefficient, which is somehow most informative about what is explaining my data. and I'm setting the rest 0, but I set this one, and I pick this one coefficient as a good guess. Right? And then I pick the next and then I factor that out, and I pick the next coefficient that is most informative. Okay, so we're going to kind of use a similar idea to this, but now involve the geometry of this L1 norm on the space. Okay. Okay, so the real trick here is I'm going to draw the space for alpha in multi-dimensions, right? So now this is the space of, this is alpha in Rd, in this case d is equal to 2. And now the function is going to be kind of coming out this way. All right, but now once we get to 2 dimensions, we actually start to see the geometry and what's going on with the L1 norm and the L2 norm. All right? Okay, so we're going to say that I'm going to look at this formulation again, where I want to say arg min alpha x alpha minus y L2 plus, and I want to look at this version where it says such that alpha 1 is going to be less than or equal to t for some value t. Okay, let's start. Actually, let me write these in 2 different colors. This will be alpha here such that alpha 1 is less than or equal to t, and then for the ridge version, it's alpha, the 2 norm is less than or equal to t. Okay, so what I can do is I can, the same way I did with when I looked at these metrics before, so this can be a distance of t from the origin, right? This point would be alpha is equal to 0, 0. Right, this is alpha. This is the distance of t in the x-coordinate. I can go, this is t in the y-coordinate, and then I can go negative also. This is minus t, this is minus t here. Okay, so and then I can go and draw the, let me start with the L2 ball. Remember the L2 ball in this space looks kind of like this. It's this nice circle. This is like in this space in here is alpha 2 is less than or equal to t. This was the L2 ball. What does the L1 ball look like? Do you remember? It's the rhombus, right? So the L1 ball is going to look like this. And so this space in here is alpha 1 is less than or equal to t. Right, so I've got slightly different balls here that describe this restriction on this, the norm of my coefficients here. Okay. Now let's say that, see if I can choose a good point here. Let's say that this is alpha star with t equals to infinity, right, or s equals to 0. Right, if I had no restriction on my coefficients, I'm going to set alpha to here. This was the ordinary least square solution. Okay, so that means that so it's going to be an L2 ball, so it's going to kind of grow out in a circular way. I think maybe it can be an ellipse or something, but we'll draw it as a circle. So the closest point to here, which is inside this constraint, is going to turn out to be the solution. All right, so if I do this with the L2, let me see if this color works. You see that? Yeah. So this is the L2 solution, and it's basically, if I did it right, I'm basically going to intersect right here. So this is the solution for ridge regression. Okay? Right, so this, if I do ridge regression, I can solve this as a closed form. I think it's directly shrinking down towards the origin in a certain way. There's some closed form solution for this. Okay, so the first thing I notice is that if I use the L1 instead, okay, it means that my space is a little bit more constrained. So I'm going to draw this ball as well. And let me draw this color. Okay, so where is this ball going to look? It's going to be a little bit bigger. I have to be a little bit further away. Can you see that color? Yeah, or should I do something else? Okay, so it's going to look like this, and I'm going to, make you wait for it as I come all the way around the mountain here. And the solution is going to be right there. This is the solution for lasso. What's special about that solution?
It's also a solution for the L2.
It's a viable solution for the L2. Yeah, that's fine. I could have just changed what the value of t was, right? So,
Along the axis, it's more pointy, it's like closer to L2, so it's going to tend to be on the axis.
yeah, so it hit the corner of this L1 ball. This is not an accident. It exactly hit the corner. What's special about the corner? What are the coordinates of that corner right there? So the coordinates of this, the first coordinate happens to be, it's in 2D, happens to be t. The y coordinate is 0. The solution, the alpha solution, alpha 2, is exactly equal to 0. Right, so my alpha is where it matters. If I hit them exactly on the coordinate axes, the corners of this ball have zeros for some of the coordinates. Right, and this is kind of the magic encoded in the geometry. That the L1 ball, when you kind of find the best solution in this space, they tend to be on the corners. Now, in high dimensions, you need to kind of twist your brain a little bit, and this is kind of a pointier rhombus, and there's kind of a point coming out this way, and then there are these ridges that kind of come along the end here, are these kind of, and so, like along the, if I had a z coordinate, it was in 3 dimensions, right? Let's go stand up here, right? Okay, so I've got the z dimension coming out here, and there's an edge along here that it could also hit, right? The ball, if it's over here, it could hit this edge. Well, that still has the y coordinate as 0, but the x and z coordinate are non-zero. That still gives me one of the coordinates as 0, the other 2 are not. And then it's, in a lot of cases, it'll give more and more coordinates 0. Right? Whereas the L2 ball, the L2 kind of generalization, okay, it shrunk all the coordinates. They're all closer to 0. But there's no thing special that actually snaps them exactly onto 0. So the actual solution to the L1 regularization problem is exactly a bunch of the coordinates become 0. So it's saying if the coefficient for something is small, you might as well snap it all the way to 0. And this is kind of the mathematics of the way we set up the formula kind of does this as its actual solution.
I have 2 questions. The first one, I'm kind of confused about why you drew circles around alpha star.
Yeah.
What's that supposed to represent?
Okay, so these aren't necessarily circles, but there's some sort of these are this part of the cost function here, right? So it's the part. So this is the minimum of that cost function. It's the same for both of them, right? And it's kind of these concentric ellipses of some form. Right, and I want to find the minimum solution such that this is satisfied. So I'm kind of growing, think of growing these parabolas with this as the center, right? And where did the parabolas first hit here? What's the lowest point on the parabolas that hit there? You can imagine that by drawing these concentric balls around them where they all have the same function value until you hit this feasible set, the allowable set of solutions.
Okay, my second question is, here we have L1 and L2. Has it been tried to do L anything else, maybe like less than 1?
Yeah, okay, good. So you think, okay, L1 biases towards, what you really kind of want is L0. You want to just minimize the number of non-zeros. The problem with that is L1 and L2 are both convex solution spaces. L, say, 1/2. Remember, if you remember, we discussed L 1/2 looks something like this. This is right. So this would be the L 1/2 ball. This is not convex. Okay. So the problem in trying to optimize it, say I've got my parabola coming out here. It kind of becomes like one of these hard combinatorial problems. I don't know immediately which one it's closest to. There could be many of these points it's closest to. Whereas convex solution, I can plug in some gradient descent type approach, or these other things that work when the domain I'm searching over is convex, everything works fine. When the domain I'm searching over is not convex, it becomes kind of tricky. Right, I start with the solution here, I walk this way, I hit here, do I go this way or this way? I don't know. And in high dimensions, there are even more of these choices you have to make, and it becomes problematic. There are other convex things. There's like, people looked at this, what is this? If I get this right, L1 minus L2, no, the L2 minus L1 norm is something that has some neat properties, and there are other sorts of regularization people put on this. There's like, if you look at this as, you can look at, when the solution is like a matrix, people have looked at things where you look at the nuclear norm or other sorts of norms on these coefficients that people looked at. And these have other nice properties. The L1 is kind of the simplest that has these magical effects. Yeah. And the L2 is the one that has a closed form solution. So those are kind of the two kind of pinnacles, but there are other ones that have found uses in places. Okay. Okay, so now so this is kind of what's going on. There's one more kind of cool thing to think about, which is, it turns out that I said this orthogonal matching pursuit algorithm is kind of a fairly simple way of doing this that gives reasonably good answers. Turns out there's a way to solve L1 regularization in basically closed form that usually runs in polynomial time, called least angle regression. And I'm not going to describe this example in full detail, but I think it's kind of useful to kind of think about what it's doing. And the idea is it's going to, I've got a picture here. Okay, that was drawn more carefully, but I think I did pretty well. Okay, so least angle regression. This solves lasso exactly, and it does so for all values of S or T. Okay, so not only does it solve it, but we have this choice of you have to choose some value to kind of say how important is the regularization. Some S or some T value, depending on the form I used. And so, I don't know how to choose that value. And if you just choose it arbitrarily, then you might get into trouble. The nice thing about this is it solves it for all values of this. And basically what it actually does is it starts with T equals to 0. It it solves it, right? And then it increases t while maintaining the optimal alpha sub t. All right? That should say optimal. Okay, and so to think about this a little bit, what's going on here? I've got my alpha star here, which is my optimal. This is the ordinary least squares solution without any regularization. That's when t is infinity. So say t equals infinity. What is the solution when t equals 0? Or when t equals 0. Right? So it's x alpha minus y. Such that, so the origin. So if t equals 0, the solution is here. This is t equals 0 solution. Okay? Okay, good. So this, when t equals 0 solution, this is easy. This is kind of a base case in a recursion. What happens as t is increasing? What's the first thing that happens when t is increasing? Right, so let's say I increase t a small amount here. Let's say this is t equals, say, 1. Right, then what's the solution going to be? I think it's a very small amount. It's some very small increase in t.
0, 1, 1, 0.
Yeah, so what's going to happen is the solution here, right, is going to have, what's interesting is that it's going to have exactly one non-zero coefficient initially. As it moves away from the origin, it's going to start with having all 0 coefficients, all the alphas are 0, and then as it starts moving away, at least at the very beginning, unless some weird degeneracy happens, it's going to have only one of the coefficients is going to be non-zero. Right? So the solution here is going to be t0. Right? So as t grows, it's going to move linearly as a function of t. So that's the other neat thing, is that this changes linearly with t. So as t increases, this changes in a nice linear way. Okay, and then at some point, and if it's a perfectly symmetric thing here, there's some ball around alpha 0, I'm going to keep growing this until there's some magical point here where at this point it changes. Right? At this point, let's call this value t1, and then the solution is still t1 0, but then from here moving forward, as I keep increasing, the solution is going to move in this way. And again, it's going to be a way that's linear again. So between t1 and we'll call this t2, I'm going to get exactly alpha 1 star, alpha 2 star. And it's going to move in a linear way. That means I can write down a linear equation as these are increasing. And the sum of the coefficients, and this is where the L1 is important, the sum of the coefficients is going to add up to exactly t. The sum of the absolute value of the coefficients. All right, so I can trace out the path of the coefficients. It's going to come here, and that's going to make a path down here, and it's going to stop. And the line in this d or d plus 1 or two-dimensional space is going to be a bunch of these piecewise linear segments here. Okay, and so what this algorithm does is it says, okay, I'm going to, I can basically find whichever coefficient is increasing the most, and that is going to give me the first one, the same as orthogonal magic pursuit is the first step. Right, but then I need to solve, I can actually solve for, I can set up a set of equations and say, when is the first time when the cost of increasing along this dimension is, it kind of matches the cost of increasing along this dimension? Or how much do I gain in increasing this function as I'm moving along this line? And I can, it turns out there's an equation, a quadratic equation you can solve for this exact value of t, where this change happens. And then you can figure out what this next linear step is, and this is in d-dimensional space, and you add, at most, one coefficient at a time. Yeah?
What is called angle regression? Is angle?
I'm not entirely sure. Yeah, this is the name of the algorithm. There's a different picture of this I can show. I don't know if that helps, but okay. So this, and because I've only had these, it's only because this is a linear path I can solve for when the point's going. Now that, yeah, I'm not sure where the angle comes from. There's another picture of this going on here, where. So this is, on the y-axis are going to be all the alpha values. Alpha 1, let me draw this in different colors. Alpha 2, alpha 3, and so, and then the x-axis is t, and so let's say that alpha 3 is the first one that has a non-zero coefficient. It's going to initially go up at a slope like this. So as t increases up until value t1, it's going to be increasing in this way. Okay, after this, it might be, maybe it's still increasing, but the slope decreases. And I'm going to have something else happen in that alpha 1 coordinate is now also going to be increasing. And the slopes need to add up, the absolute value of the slopes need to add up to t. Right? In the first case, or need to add up to 1. In the first case, the slope is 1. In this case, maybe it's 1/2 and 1/2. It could be 1/3 and 2/3. That's also fine. Right? And then this happens until some point t2. And then I'm going to have, you know, maybe this goes up, and this way, this is now alpha 2, but what happens, I guess that's too high. This is, it's the alpha 2, maybe this continues in this way, and this one is going to actually be decreasing. Okay, and it could be strange things. You eventually say, if I pick one variable, T1 gives me, whichever, alpha 3, this gives me the best fit. But if I keep going further on, what's going to happen is I'll get a better fit by setting this to 0 and using these two expressions. And so you need to kind of keep running at this, and these bounce all around. Okay, now, if you always only activate variables, then this takes polynomial time. You sometimes need to deactivate variables. And then you might get, it might run an exponential time, and there's some, probably never happens, but it could happen. Okay, but you can run this, and you need to, if something crosses 0, you want to snap it to 0 until it becomes activated by the same test again. That's technically the right way to do it. Most people, if it goes through 0, I just make the coefficient negative. That's also fine. It's perfectly reasonable to have a negative coefficient. And you can trace these things through here like this. Okay, so there's I wrote out some like pseudocode in the notes you can look at if you want to, but this is basically what it's doing. And it can solve for this sort of exactly, and then you're solving for all values of t, so effectively that's equivalent to solving for all values of s. You don't necessarily know the correspondence between them, but you can, you've got a solution for each of those, yeah.
So then do I just look at all the values with the various t's? Like how do I pick which t I want to use for my...
Right, so that's a good question. So the answer will come in 3 lectures, or it can say we're going to use cross-validation. Okay, so we're going to hold out some data, and we're going to do this on some of the data, and then on the other data points, we're going to evaluate how well the L2 score is. And we'll talk through this much more in 3 more lectures, which in the old order was the next lecture, but I switched things up. So, okay. Right, so we'll choose it with cross-validation later on. You can use cross-validation for a bunch of other stuff, but this is one of them. But now we have all the solutions, and now I can track the cross-validation score as I go and find the minimum. Okay, so hopefully you kind of believe that this works, right? You get some mathematical geometric view of what's going on. I think it's pretty cool. All right, so we're going to switch gears a little bit here and talk about we're going to talk about p-values and kind of some problems with p-hacking. Okay, so who had a chance to at least read the first couple pages of the article? At least, okay. Well, it's okay. We'll still be able to have a discussion, I think. I'm hoping, I mean, I didn't expect you to read the whole thing. It's like 17 pages, but first couple, okay. So next time. I know this is right before break, so. All right, so who knows what a p-value is? Okay, and who can explain what a p-value is? There's this cool clip on 538 where they go to some academic conference and they ask a bunch of the scientists there to explain p-values, and they're all like, yeah, I'd rather not. So, yeah, I'll let you take a shot.
I think, I can't remember for sure, but isn't it like how well the data fits like a regression on the data?
No, but good. That's a common mistake. We'll go through it. Thanks for answering. Maybe I'll try again.
You have a particular value from a distribution. It's likely that you would have a value higher than that.
So kind of that's in the right direction, but you've missed some stuff which a lot of people miss, and it's important. Okay, so in order to define p-values, you need to start with a distribution, and what does this distribution mean, right? So you need to have this null hypothesis, often called the H0 distribution. And what this is saying is, I think that I'm observing data, and I think that the data is going to be observed under this distribution. This is what is the commonly accepted model of the world that fits this data. Like, I think the average score on my test is going to be 80, and it's going to be a normal distribution with a standard deviation of 10. Right? I could say that that's my null hypothesis. There are issues with going above 100 and below 0 and so forth, but let's kind of just set something simple. There's some distribution that I believe is the case, right? This is my H0 distribution, okay? And then the p-value has to do with how some observed data interacts with this distribution, right? So I believe that the scores are going to be distributed this way, and I observe something that happens here. I observe a score distribution or a particular score that looks like this, or maybe this is a particular student based on their past homeworks. These are their distribution of scores. They did this. I want to say if they scored too high, maybe they were cheating. If they scored too low, maybe something was going on, and I should in their life, and I should consider giving them some leeway or something like that. But this seems like that might be reasonable, right? And so the p-value has to, given some null hypothesis about the world, I kind of want to say, how does the data interact with that? And technically, it's going to be this area under this part of the curve. The data that's more extreme than this, right? So this area under the H0 distribution is the p-value. Okay?
So each student would have a p-value?
Sure, yeah. I mean, it could be various different things. But yeah, say I fit a model for one particular student, I assume that they have this distribution. We'll get into some of these tricky issues. Yeah. Okay, so this is kind of what the p-value is, and it's a way of measuring your observation against a given stated hypothesis. Okay, and this is used throughout sciences, especially like the biological sciences and so forth. They run and they collect data and they want to say, I observed something, this is the known belief about the world, or some sort of default belief, some simple explanation. I observed data, is this significant? Is this data significantly different from what we believe the data, the basic model to tell us? And often you say, if the p-value is less than equal to 0.05, some magical number that people come up with, you say, then you say it's going to be, the observation is somehow significant. Right? And this often is associated with rejecting the model, the H0 model, and you have an H1 model which maybe fits better. And that's some way how you can kind of come up with this score. The score could be something more complex than just a score in a test. It could be some likelihood score that you can come up with in various ways. So one model versus another model. Okay, and so there's a nice graphic I found on Wikipedia. Where like this is basically the same picture I drew, and it points out this important thing that this is about an observation given a hypothesis. It does not say anything. It does not, say anything about evaluating the probability of the hypothesis that's given the data, right? So it's not exactly the same thing there. Now you can relate these together sometimes through Bayesian statistics or through Bayes' rule and so forth if you have more data, but it's not exactly talking about hypothesis giving the data. Now the reason I point this out is in what we talk about in this class and say in a machine learning class, the hypothesis is basically our model. It's basically alpha, right? It describes our parameters of our model. So we're not really evaluating the parameters of the model in this. We're saying, given a model, how likely is observation to come from that? Now this often, you'd have to build some uncertainty and say, I believe there's linear regression and then there's Gaussian noise off that regression and so forth. You'd have to add a little bit more to do this properly here. But it's not doing this latter one, evaluating the hypothesis, which is kind of the view of the world we're taking. It's kind of saying, given I believe that there is a regression that explains things, now I see a bunch of data. Did this data way outside the pattern of this hypothesis? And that might mean that the data I observed came from a different distribution than how you built that linear regression. Or it could mean that that linear regression was wrong. It was predicting the wrong thing because the data is outside the scope of what I had measured on before. Right, so it was the wrong model. But it's sometimes you can reject the hypothesis, but you're often just saying that my data is somehow significantly different from what I would like to say, or is not. Okay, so so do you feel a little bit better about p-values now? Okay, you can take like in our department, here there's some classes like in the psychology department, math, was it 2080? Or is it math 3080? Is an applied statistics course, 3070 and 3080 talk about this in an applied way, and they're pretty decent classes. There are higher up classes that talk about the mathematics of saying, how do you properly do these significant tests for like things like linear regression, which is more complicated. Okay. Okay, this brings us to the next kind of issue with p-values is multiple hypothesis testing. So who's heard of multiple hypothesis testing before? Oh, okay, a little bit. Who reads XKCD? And who's seen this particular comic before? No, you haven't seen. Okay, this one is one of the classic XKCD comics. Okay, so this kind of demonstrates this problem called p-hacking. Okay, where people can generate things that look like they're significant, small p-values, when really it's just kind of a function of how they interact with the data in an inappropriate way, as we'll see. Okay, so there's these, okay, let's go through this. This lady believes, has a H0 hypothesis, that green jelly, she has this H0 hypothesis that so that jelly beans cause acne, runs to scientists, go investigate this. You know, I have a hypothesis about the world. They go and they investigate and say, no, the p-value is greater than 0.05. What you observed is not significant from it not causing acne under some model. All right, that sells it. Oh, but I hear it only from a specific color. Okay, so they say, well, there's no link between purple jelly beans and acne. Okay, but let's keep trying. No link between brown jelly beans and acne. No link between pink jelly beans and acne. And they keep trying these different color-specific tests. Eventually, they do this, let's say 20 times. And if you notice, there's one of these here where they're like, whoa, green jelly beans, the p-value is less than 0.05. Or if you can't read it here, p, I think that doesn't help. P is less than 0.05 for green jelly beans. Right? And so they're like, whoa, let's go and write a paper about this, right? Let's go publish this in Science. Let's take them off the market. Who knows what we're going to do, right? And so they did this, and they ran an experiment with green jelly beans, and they found this. Okay? So, right, so they write this up. Right, 95% confidence with each some terms. Okay. All right, so what's wrong with this?
So even though there's only a 5% chance of coincidence, they did it so many times with different things that goes way up. So like they like found one saying there's a low chance of coincidence, but really like it wasn't that low.
Yes. So that's exactly right. Right. So how many trials did they run? This was 4 by 5. That's 20 trials. What's 1 out of 20 equals 0.05. Right? So you would kind of expect if you ran this 20 times that one of them might come back and say, okay, this occurred only 5% of the time something this extreme would occur. Well, lo and behold, 5% of the time something this extreme occurred. Right? So it's not really coincidence when you factor this in. And this is known as the multiple hypothesis testing problem. Okay, where you run a bunch of trials over different hypotheses and you say, if you find any one of them is significant, you might declare it significant.
Sorry, so here they're using the same data always for all those trials?
In this case, in the cartoon, my guess of what they're doing is they actually they collected different data every time. We'll get to this though. That's a good point. But even here, they went and collected new data for each experiment from the same kind of they went to the same jelly bean factory and pulled out just one color. Right? Yeah.
So what about the effect of other aspects that might happen on an experiment, right? We might consider only one aspect, but when it is viewed in conjunction with another aspect, the results might change.
Yeah, so you can have these confounding effects and so forth. Let's say they controlled for all of those. This is still an issue, right? I controlled for all effects. I did, you know, they did an experiment on 1 million people in the population, and they made them close their eyes, and they put either a jelly bean of a specific color in, or just some jelly bean that had no coloration in it, right? And for half of the population one, half the other, the person who did it was colorblind, so they couldn't tell which was which, but someone recorded it, and then they measured this afterwards. They accounted for all these factors. You know, proper scientific method, all that good stuff. This is still a problem. Yeah.
So does that mean if they run those set of trials like one more time, that the other colors can also be like can replace the green color?
Yeah, right. So they could, let's say they started from scratch again. Another group of scientists said, I want to go and reproduce this study. And they go do the same study with the same colors, but with different people, different actual jelly beans, right? And they find a different color causes acne. This would actually be, that's a good thing. When scientists reproduce studies and they find a different one, but this one is not significant, that tells them something useful, right? How do you combine these things together? This is becoming an important area of science. How do you do these meta-studies across many of these smaller studies? How do you combine together the effects? Yeah, so this is a good thing to do, and some scientists are doing this. We'll get to this.
So like along those lines, wouldn't with peer review this no longer be an issue, because other people would try to like replicate this and they wouldn't be able to? So
You have a very kind of idealized, magical view of how peer review actually works. So peer review is often done by like people, you know, someone not too different from me, right? Or maybe my grad students in some cases, right? And I have a lot going on, right? You know, I'm teaching this class, I'm trying to run my own research program. I'll get papers to review, and I read them, and I do my best effort in the 2 hours I have to spend on peer review, right? I do not have time on a peer review to go and replicate the study, right? So I have to read it, and I kind of, if I see that they did this and I believe they ran many colors, and then they're only reporting one, I should be suspicious as someone who's statistically kind of minded about this, right? But if they only report this, say someone came running and screaming and said green jelly beans cause acne, and we tested just that, and we found this, then maybe that's reasonable, okay? Then I may accept it, but if I have reason to believe they tested more things, and we'll get into this, then this I would be skeptical of, right? Okay, so this is kind of a data science pipeline, and kind of don't worry about all of this, but like you run many trials, and some of this is success, and so this has been going on. This has been how, like, science used to work, where you would kind of come up with one hypothesis and test it, and like Fisher developed the statistics for doing these things the proper way, but scientists have been reusing data sets. They've been many groups are trying to study the same problem. So you may have 20 groups have the same internal hypothesis. Wouldn't it be great if this drug that's cheap to produce would cure cancer? 20 groups try it. One group individually said, I found it did significantly have a positive impact on cancer. They publish it in Science. The other 19 groups had a negative result, so they don't publish it, right? So around 2005, this guy John, not sure how to pronounce his last name, so Ioannidis or something. So he did this big study of papers published in top journals. I forget whether it was Science or Nature or something like that, and did reproduction studies and showed that many of them were false, mainly because of this reason. that different groups were looking at the same problems. The ones that succeeded were the ones that got published. Right? And this caused a major stir. This caused kind of a major stir, and it kind of made people rethink, how do we do science in this case? Okay, and there are a couple of solutions. One is what's called this Bonferroni correction, and that's a way of saying, okay, if I have 20 hypotheses that I'm going to check, I can be conservative and say, whatever the p-value is, I need to divide that by 20. So I need it to be, if I have 20 hypotheses, then I need p to be less than or equal to 0.05 divided by 20 for this to be true. And this will be conservative, and you'll only report things that are really truly significant. It's often too conservative. So if you have a lot of hypotheses, like a big hypothesis space, like in a machine learning or data mining problem, where you're searching over infinite hypothesis space, this is not possible to do, right? But in some cases, you can do these Bonferroni corrections.
So you will say that this is a misconception of the p-value usage? I mean...
well, a lot of people do not state what their hypothesis is at the beginning. Let me try and formalize this based on the reading I gave you, and that's what I'll do next, right? So there's also things where people try and state their hypothesis ahead of time. And so if you state it ahead of time, so you can, so people post, I'm going to run this experiment, and I'm going to have this hypothesis, and then people can keep catalogs of these. And then if it doesn't turn out, it gets put in some archive, and maybe it doesn't get in a giant science or journal, but people can take this into account for Bonferroni corrections and stuff like that. Okay. So the main thing about this paper I had you read, and this was by Gelman and Loken, and still pretty recent, so 2013. They said this p-hacking problem is more serious than people actually anticipated, and people do it accidentally all the time, even when they think they're accounting for all these things. And they said there are 4 ways to kind of set this problem up. Okay, so one is there's there's exactly one kind of reasonable H0, and then it's kind of clear what the hypothesis test is that you do and the p-value. This one is kind of the setting that was formalized by Fisher around 1905 or something like this, and this one is clearly okay, right? If there's only one possible hypothesis you could make about this, there's no issues. The other one is that you state or you pre-register the hypothesis, and not only the hypothesis, but also its parameters, right? So I say I've got a null distribution. This is my H0, and it has a mean and it has a standard deviation, right? So I set these ahead of time. This is also okay, right? If you pre-register this, or before I collect my data, I'm going to do this, and I'm only going to report these findings by themselves. I'm not going to combine them with anything else, say for my same data set or the same set of trials I'm trying to do. And then the 4th one down here is p-hacking, where I search the parameter space for some low p-value. So basically, I can look at some previous data and try and say, well, if I set, if I have some, you can view it in this land. If I make an observation here well, maybe the p-value is a little bit too large, but if I instead search and set my null distribution h0 prime over here, well, now it becomes significant. Right? In this case, this is clearly wrong, but there are situations where, say with the green jelly bean case, I keep searching over a different test to do. And that's kind of thinking, I'm taking a test, I'm restricting it to one dimension in some dimensional color space or something, and in that space, one dimension is going to look significant. There's different variations of this, and this is clearly p-hacking. This is bad. What a lot of people end up doing, and this is kind of accidentally, is they fix the test. They fix the hypothesis test they're going to do ahead of time. They say, I'm going to look for certain classes of jelly beans which are causing acne. There's some paper, there's something that they discuss where they found if there was some sort of effect if people were wearing red or pink. If they just did red or just pink, then they didn't report it. But they said if it was red and pink, then they found this to be interesting. And so if someone comes to you because they have experience and they say, well, I think that if they wear black, I'm not going to get this effect, and if it's red or pink, it is. And then they look, well, anything against black, red, and pink go. Like you can kind of use data. If you use your data to set the parameters of the hypothesis test. So if I don't adversarially try and find something just to get significance, but I say, well, I let the data guide me to kind of say, how do I set up a test? I look at the data, I say, here's a good null hypothesis by looking at it, and then I collect more data and I compare it to that. That ends up being this third type, which is also bad. Right? So this one is clearly bad, and this one is also bad, and people do this kind of on accident. Okay, so I've kind of run out of time, but if you're interested in these kind of issues, this is a fairly recent kind of observation, and this leads to still after this 2005 paper, this still leads to a lot of issues with bad science being published. Okay, so in machine learning and data mining, cross-validation is kind of going to be our answer to some of these things, and we'll talk about that in a few minutes. Yeah, but you can't change it. Right. But that's not real.